Hey everyone, welcome to this hands-on lab on creating a basic Amazon VPC setup using Terraform. In this video, you'll learn how to set up Virtual Private Cloud, VPC for short, which is a foundational component for building your cloud infrastructure. We will walk through the process step by step, ensuring you understand each component and its role in the overall architecture. By the end of this tutorial, you'll be able to create a secure and scalable VPC with public and private subnets, an Internet Gateway, and a NAT Gateway as well. The prerequisites for this labs are basic knowledge of networking, AWS and Terraform, AWS CLI and Terraform installed and configured in your machine, and lastly, AWS profile configured with permissions to Amazon EC2. Let's start by understanding what we will be building in this hands-on lab by going over the different components. First of all, we have Virtual Private Cloud, VPC for short, which is a private network within the AWS cloud where you can launch AWS resources. It provides you with control over your virtual networking environment, including IP address ranges, subnets, route tables, and network gateways. Within our VPC, we will create both public and private subnets. Public subnets will have direct access to the internet. We will place resources here that need to be publicly accessible, such as web servers. Private subnets, on the other hand, will not have direct access to the internet. Instead, they will use NAT Gateway for outbound internet traffic, making them ideal for databases and application servers that don't need to be directly accessible from the internet. Next up, we have route tables, which contain a set of rules called routes that use to determine where network traffic is directed. Along with route tables, we'll create route table associations, which link subnets to their respective route tables. To allow resources within public subnets to communicate with the internet, we need an internet gateway. It acts as a bridge between your VPC and the internet. Now let's talk about NAT Gateway, which I mentioned earlier. A Network Address Translation Gateway, or NAT Gateway for short, enables instances in private subnets to connect to the internet or other AWS resources while preventing the internet from initiating connections with those instances directly. This is crucial for maintaining the security of resources that should not be exposed directly to the internet. To ensure that a NAT Gateway can access the internet, it needs a public IP address. We achieve this by associating an elastic IP, EIP for short, with NAT Gateway. An EIP is a static, public IPv4 address that is reachable from the internet. EIPs are especially useful for instances or gateways that need consistent, unchanging public IP addresses, such as when you want to allow inbound traffic from the internet to a specific instance or enable outbound traffic from the instances in private subnets via NAT Gateway, which I've just described. As I mentioned earlier, we'll use Terraform, an infrastructure as code tool that allows you to define and provision your infrastructure using a high-level configuration language. Terraform makes it easy to manage your infrastructure through a version control, allowing you to replicate and modify your environment with ease. So here are the steps we'll be taking. First, we will declare variables for CIDRs and availability zones. Then we will declare the VPC and subnets. After that, we will move on to Internet Gateway and public route table, and then we'll declare elastic IP, and that will be the end of the public infrastructure. After that, we'll start with the private infrastructure and we'll declare NAT Gateway and private route table. Finally, the last thing we'll declare will be route table associations to connect the subnets to their route tables. Prior to starting the actual lab load, we must set up our Terraform AWS configuration in the config.tf file. The configuration file consists of the required version, required providers, and backend declaration. Let's briefly discuss each one. The required version is a constraint that tells the Terraform which version of Terraform can be used in this setup. The required providers specify the providers required for this lab, which is only AWS in our case. A provider is an entity that provides configuration for a particular resource or group of resources. For example, a resource can be AWS VPC or AWS Subnet. And lastly, the backend declares configuration for storage where your Terraform state will be stored. You can always store the state file locally, but if you want to collaborate with other people, it is a good idea to have a central resource such as S3 act as a shared medium. If you want to learn how to set up the backend, please visit our Setup Terraform with S3 backend video. Now let's start the actual lab by declaring variables. Variables consist of three arguments: type, description, and default. The type defines the kind of data that the variable can hold, which can be string, number, bool, list, map, set, object, or tuple. Description informs what the variable is used for. It helps provide context for others or for yourself in the future who may read the code. Default argument provides the default value for the variable. If no value is provided, when the variable is referenced, Terraform uses this default value. Otherwise, it will ask you to provide the value yourself. In this lab, we use three different types of data for our variables: string, list string, and map string. A string is a simple text value. In this example, the variable VPC underscore CIDR underscore block holds a single string value representing the CIDR block for the VPC. CIDR blocks are pretty much the IP ranges. A list string is an ordered collection of strings. The list can contain multiple string values. Use list string when you need to store multiple related string values in a specific order. In this example, the variable availability zones hold a list of strings, each representing an availability zone. Lastly, a map string is a collection of key-value pairs where both keys and values are strings. The keys are unique identifiers. Use map string when you need to store related string values that can be identified by unique keys. In this example, the variable public subnets holds a map where each key, for example A or B, corresponds to a string value representing a CIDR block for a public subnet. In total, we have 6 variables. The first one, VPC CIDR block, just defines the CIDR block for our VPC. In this case, it's 172.20.0.0/16, which specifies a large number of IP addresses available for use within our VPC. Similarly, the public and the private subnets have their own CIDR blocks, such as 172.20.48.0/20 for one of the public subnets, which defines smaller specific ranges of IP addresses within the overall VPC range. Then we have availability zones. An availability zone is an isolated location within an AWS region. Each region consists of multiple isolated locations, and we specify availability zones to ensure high availability and fault tolerance for our infrastructure. The variable availability zones is used to list the AZs where our subnets will be created, such as US East 1A and US East 1B. By distributing our subnets across multiple availability zones, we ensure that our resources remain operational even if one of the availability zone experiences an outage. Then we have public and private subnets, CIDR blocks, as I mentioned earlier, which define their appropriate IP ranges. As you can see here, we have two different subnets in each public and private. As you can see here, we have two different CIDR blocks for both public subnets and private subnets. We have public subnet and private subnet variables which map our subnets to availability zones. Lastly, we have whitelisted IP, which I'm actually not going to use in this lab, but in the following lab, so stay tuned. Now that the variables are set up, let's begin with setting up our resources. Let's continue on with creating a file called main.tf. In this file, that's where most of our resource declarations will be. First, let's start with declaring the VPC itself. So resource, AWS VPC, we'll name it example VPC. So here we have three different arguments in this resource: the CIDR block arguments, which specify the IP address range for the VPC. In the example, the CIDR block is being set to the value of the VPC CIDR block variable, which we've defined earlier. Then we have the instance tenancy argument, which determines whether instances launched in this VPC are dedicated to a single customer or can share hardware with instances from other customers, which is set to default. Since this is not a highly confidential application, we're just going to leave it as is, meaning default. Lastly, we have the enable DNS hostnames argument, which controls whether instances launched into the VPC get public DNS hostnames. This means instances will have a public DNS name that can be resolved to the instance's public IP address. This is useful for services that rely on DNS hostnames. Now that we have declared VPC, let's move on to subnets. We will begin by declaring private subnets. For VPC ID, we can reference the resource we've created above. As you can see here, we created the resource for private subnets, and we've named it accordingly. The VPC ID argument specifies which VPC the subnet will be associated with. This line links the subnet to the VPC created earlier, using the VPC ID. It ensures that the subnet is part of the example VPC we just defined. The count argument determines how many instances of this resource will be created. This line uses the length expression to set the count. It calculates the number of private subnets to create based on the number of entries in the private subnets variable, which is a map in this case. For each entry in the map, a separate subnet resource will be created in its own availability zone. Just as the VPC, we have the CIDR block argument, which specifies the IP ranges for the subnet in the form of CIDR block. Lastly, the availability zone argument specifies the availability zone in which the subnet will be created. This line assigns an AZ to each subnet by selecting an element from the availability zones list based on the current count index. This ensures that each subnet is distributed across different availability zones, which enhances fault tolerance and high availability. Imagine you're setting up a highly available web application with both front-end and back-end components. The front-end servers, which need to be accessible to the user over the internet, are placed in public subnets. These public subnets distributed across different availability zones allow the service to directly communicate with internet through an internet gateway, ensuring users can access your application from anywhere in the world. Meanwhile, the backend servers, which need to be isolated from the public internet for security reasons, are placed on private subnets. These private subnets are also spread across multiple availability zones to ensure that your application remains available even if one availability zone fails. This combination of public and private subnets, each with its own IP address range and role, provides a high availability and secure architecture that keeps your application both accessible and more silent. And here I will just paste the same resource for public subnet instead of typing it out again. Now that we've declared our subnets, let's move on to declaring the components of the public infrastructure. We will start with Internet Gateway. This one is pretty straightforward. The only argument it has is the VPC ID, and this attaches it to the VPC we've just created. Internet Gateway will allow our VPC to access the internet and be accessed from the internet as well. Next, we will create a route table, which we will use to associate Internet Gateway with the public subnets in our VPC. As before, we need to specify a VPC ID to link this public route table with our VPC. After this, there is an argument for route, which contains CIDR block defaulted to 0.0.0.0/0, which represents all IP addresses. Essentially, this route directs all outbound traffic to the specified gateway. Next, we have gateway ID. This line links the route to the internet gateway created earlier, enabling internet access for any subnet associated with this route table. The last resource of our public infrastructure is elastic IP address. EIPs are necessary for NAT gateways to provide outbound internet access to instances and private subnets. Now let's look over the arguments. So we have count, which ensures that the number of EIPs created is equal to the number of private subnets, in turn ensuring each NAT gateway has an EIP. The VPC domain ensures that the EIP is compatible with the VPC and can be attached to a NAT gateway or an instance within the VPC. Finally, we have depends on argument, which ensures that the internet gateway is available before EIPs are created, preventing any potential issues with routing internet traffic. Now that the public side has been set up, let's create a NAT gateway to allow our private subnet instances to connect to the internet. Let's go over the arguments. The count argument determines how many instances of this resource will be created. Terraform will create as many NAT gateways as specified by the count value, which in this case is the number of public subnets. This ensures that a NAT gateway is created for each public or private subnet because here we have the exact same number. The logic here is that each private subnet needs a NAT gateway to route traffic to the internet securely. The allocation ID argument specifies the ID of the elastic IP to be associated with the NAT gateway. The element function retrieves the corresponding AIP ID from the AWS AIP.NAT_AIP resource, ensuring that each NAT gateway has a unique IP assigned. The subnet ID argument places each NAT gateway in a public subnet. The element function ensures that each NAT gateway is placed in the correct public subnet corresponding to the current count index. Placing the NAT gateway in a public subnet is crucial because it needs to communicate with the internet. Finally, we have depends-on argument, which ensures that the internet gateway is fully created before the NAT gateways are set up. This dependency is needed because the NAT gateway requires the internet gateway to route traffic to the internet. Now let's continue on to setting up the private route table. Let's copy this block that we already have, and we will simply reuse it. The private route table is very similar to the public one with a couple of distinctions. Since we have multiple NAT gateways, the count argument ensures that a route table is created for each private subnet. Furthermore, in the route block, instead of gateway ID resources, we will use NAT gateway ID with element function to retrieve the IDs of NAT gateways created in the previous resource. Now, the last two resources we have to create are AWS route table associations for public and private subnets. In AWS, subnets do not automatically use any route table other than the main route table unless explicitly associated with another route table. These resource blocks ensure that each subnet, public or private, is properly connected to the correct route table. The resource consists of three arguments: count associated to the number of subnets, route table ID, which specifies the route table to associate with the subnet. All public subnets share this single route table because they all need to route traffic through the internet gateway. Element function retrieves the ID of each public subnet, and the count index ensures the correct subnet is selected for each iteration. The only difference for private subnet association is using element function in route table ID argument to ensure that each private subnet gets its specified route table by retrieving the correct route table ID based on the count index. Now that the code is finished, before starting with our Terraform, let's just quickly review everything to make sure we did not make any mistakes. So one thing I've got right here is, instead of specifying private subnet variable, I've specified public subnet in our private subnet resource. So let's change that quick. I'm just reviewing my code for now. In the actual video, I'll speed this part up unless I find any more mistakes that I've made. I believe everything else looks good. So let's start with applying our Terraform. So first, we will do Terraform initialize. That should download all of the plugins. In this case, it's just AWS. And also, as we can see here, Terraform finished installing our providers. It had also created a log file to record the provider selection it made. Now that Terraform has been successfully initialized, we can run Terraform plan to see any changes that are required in order for our infrastructure to be applied. As you can see here, the first thing on the list is our elastic IPs. As we scroll down, we can see our internet gateway being created and two NAT gateways, followed by two private route tables, after which we have the public route table. Following, we have the route table associations, both private and public, after which we have our private subnets and our public subnets. And finally, we have our VPC. Now that we have our plan, we can safely apply. Ensure you always run plan before applying That way you get to review what your code actually does and find, if any, discrepancies. Creating usually takes a little bit, especially for NAT gateways, so let's just wait a minute or two. In the video I will speed this up so you don't have to wait. And as you can see, all of our resources have been successfully created. And now we have the basic VPC setup. I now encourage you to log in to your AWS account and check out the resources we have created using Terraform there. Once you are done and the resources are no longer needed, you can use Terraform destroy command to remove all of them from your AWS account. So let's do that. This will probably take a minute. And Terraform destroy is the opposite of Terraform apply. You get the plan as well. However, in this case, it's the reverse. Simply type in yes, and this should proceed the operation, and in a few minutes, all of your resources will be destroyed. As you may have noticed, the resources we have created in this lab cannot really do anything between each other, as most of them provide networking capabilities for compute-type resources. In the next lab, we will be creating EC2 instance and RDS database, which will host a WordPress application. This will truly demonstrate the power of resources that we have created in this lab. So I'm hoping to see you there. But for now, let's move on to the conclusion. First of all, congratulations on completing this lab. I hope that you grasped the basics of Amazon VPC with Terraform. This diagram shows on what our current setup should look like. In this lab, you've learned the functions and how to create and configure a variety of networking resources, such as public and private subnets, an internet gateway, and a NAT gateway. This lab is a good starting point for creating scalable and secure environments in AWS. As I've mentioned, in the next lesson, we will build on top of this lab and launch our first application. If you found this tutorial helpful, please like and subscribe. And if you have any questions about this video or suggestions for future videos, feel free to drop them in the comments below. Until the next time.